Oh, hi. Welcome back to the Arcade School. This lesson deals with power supplies. Every electronic game has one or more power supplies in it. Well, what the heck do we mean by a power supply? Surely the power for the game comes from the wall receptacle. But the wall receptacle, unlike a battery like this, which is DC or direct current, where there's a positive and negative terminal, is what we call alternating current, or AC. Alternating current actually changes direction 60 times a second. Well, alternating current is great for things like weed whackers and toasters and electric hair dryers and so on, but it's no good at all for things like computers. Computers require direct current to operate, such as the direct current from the battery. Well, we know that video games and pinball machines are not battery operated. How does the direct current come from the AC? Well, that's the job of the power supply. The power supply takes the alternating current and changes it into direct current. Also, the power that comes from the wall is 120 volts or so, but the computer requires just 5 volts to operate. If we tried to connect the 5-volt computer to the 120-volt power source, the excessive pressure would literally blow the tops off of all the ICs. So the power supply also lowers the voltage for us, as well as changing it from alternating current into direct current. Let's start off by taking a look at a simple graph of alternating current. This graph shows voltage in the vertical direction and time in the horizontal direction. Any positive voltage is shown as a line drawn above the 0-volt point. Remember, 0 volts is our ground, our electronic reference point. Negative voltages are shown as a line drawn below the ground line. The time from one end of the graph to the other is 1/10 of a second. Notice that the voltage does not instantly change from positive to negative. The voltage actually starts out at 0 volts and gradually builds up to a peak positive voltage before returning back to 0 volts again. When the voltage returns to 0, it keeps dropping until it reaches a peak negative voltage that is equal to the positive peak voltage, and again it returns to 0. This is known as one cycle of alternating current, and the process is repeated 60 times a second. Notice that the voltage actually drops to 0 volts every 120th of a second after each half cycle. The graph we've made is a picture of the alternating current and is known as a waveform. The first thing the power supply does for us is to change the voltage. To do that, it uses a device called a transformer. And this is a typical transformer from an Atari video game. This is the transformer right here. The transformer is made out of a laminated iron core with a couple of coils of wire wound around it. This is the schematic symbol for a transformer. As usual, the schematic symbol is supposed to represent the part, and in this case actually looks something like a transformer. The iron core is represented by the vertical lines in the center of the symbol, and the two coils are shown on either side of the core. The coil on the left is called the primary winding. The primary winding is the input side of the transformer. On the right of the core is the secondary winding of the transformer. The secondary is the output side of the transformer. This is true of just about all schematic diagrams. Normally, schematics are drawn with the inputs on the left-hand side and the outputs on the right side. Well, let's connect this transformer to the 120 volts AC and see how it works. The primary winding is connected to the 120 volts AC through a fuse and the plug. When connected to the AC, alternating current flows through the primary coil. This creates a magnetic field that changes polarity at the same frequency of the AC power, 60 cycles per second. This changing magnetic field is picked up by the secondary winding, and current is forced along the two leads of the secondary. If you want to, you can think of the primary winding of the transformer as a kind of transmitting antenna, and the secondary winding as a receiving antenna. Although there's no electrical connection between the two windings of the transformer, there is a magnetic connection that allows current flowing in one coil to create a current in the other. But how does the transformer change the voltage for us? Well, the answer lies in something called the turns ratio of the transformer. The primary winding of the transformer might have, say, 1,000 turns of wire on it. The secondary winding might have only 100 turns. This is a turns ratio of 10 to 1. The turns ratio determines the voltage ratio of the transformer. So if we connect the primary winding of this 10 to 1 transformer to a 120 volt AC source, we'll get 12 volts AC from the secondary winding. This is known as a step-down transformer because the primary voltage of 120 volts AC is stepped down to 12 volts AC at the secondary. There are times when we need a higher voltage than the 120 volts AC from the power receptacle, such as in the Bally and Stern pinball machines, where the score displays require 190 volts DC to operate. To obtain the higher voltage that we need, we can use a transformer that has more turns of wire on the secondary than on the primary winding. This creates a higher voltage on the secondary. Transformers that have a higher secondary voltage than primary voltage are called step-up transformers because they step the voltage up to a higher level. Most games require more than one power supply to operate. Atari's Asteroids actually has 12 separate power supply voltages. To obtain a number of different power supply voltages, we can use a transformer with more than one secondary winding. Multiple secondary windings on transformers are very common. This is the schematic diagram for a multiple secondary transformer. Notice that there's a single primary input on the left and 3 separate secondary windings. And by putting 120 volts AC in on the left-hand winding, we can get 3 different voltages out of the 3 secondary windings on the right: 10 volts, 20 volts, or 6.3 volts. And here's the transformer itself. Notice the different solder tabs to which you can attach wires to obtain the different voltages necessary for the various circuits in the game. There's another type of transformer that we see all the time in electronic games. It's called the center tap transformer. When the transformer manufacturer is making the center tap transformer, he'll start winding the secondary and he'll stop exactly halfway through. He'll pull a loop of wire out and attach a small lead to it and then continue winding the secondary. The voltage between the center tap and one side of the secondary is the same as the voltage between the center tap and the other side of the transformer secondary. Here's the schematic symbol for the center tap transformer. As before, we use 120 volts AC input on the primary. But on the secondary, we have a center tap and 2 outside terminals. The center tap will usually be grounded, and as such is usually labeled 0 volts on the schematic. This happens to be a 24 volt center tap transformer, so we get 12 volts between the center tap and one end, and 12 volts between the center tap and the other end of the secondary winding. Multiple center tapped windings are just as common as multiple conventional secondary windings in transformers. We generally see 2 types. One type has 2 completely separate secondaries. Other types have a single center tap with multiple taps to provide the different voltages necessary to power the game. It's really important to note that a transformer is strictly an AC device. The transformer uses AC as an input on the primary and gives you AC as an output on the secondary. The transformer has nothing at all to do with direct current. Now that we have a way to lower the 120 volts AC from the wall receptacle to 12 volts using our 10 to 1 transformer, let's figure out something to do with it. One use that easily comes to mind is as a battery charger for a 12 volt automobile battery. Let's look at the schematic diagram of the 10 to 1 transformer with the 12 volt output connected to a discharged automobile battery. Knowing that current flows from positive to negative, according to Benjamin Franklin's concept of conventional current, we can predict what will happen in a circuit by looking at the schematic diagram. Remember, the transformer's output is alternating current. The transformer is strictly an AC device. It uses alternating current as an input on the primary and produces alternating current as an output on the secondary. So let's look at the circuit when point A is positive and point B is negative. The current flows from positive to negative. So in this case, it flows from the positive side of the transformer secondary into the positive terminal of the battery, giving it a little charge. The return path for the current is from the negative terminal of the battery to the negative side of the transformer's secondary winding. So far, so good. We've managed to give the battery a little shot of current to charge it. But let's see what happens when the polarity is reversed. When point A becomes negative, it will literally suck out any charge that was put into the battery. What we've made here is not a battery charger, but a bomb. The heat generated by the current rushing in and out of the battery will cause it to explode, sending acid everywhere. Let's try the same circuit again, but this time we'll put a diode in series with the transformer and the battery. The anode of the diode is connected to the transformer secondary at point A, and the cathode to the positive terminal of the battery. The negative terminal of the battery is connected to the transformer secondary at point B. Let's trace the flow of current when point A is positive and point B is negative. The current flows from the positive terminal of the transformer to the anode of the diode. Since the arrow of the diode symbol is pointing the same direction that the current is flowing, the current passes right through the diode to the positive terminal of the battery. The return path for the current is through the negative terminal of the battery and back to point B, now the negative side of the transformer secondary. Again, so far so good, but let's see what happens when the transformer reverses polarity and point A becomes negative and point B becomes positive. The current wants to flow from point B of the transformer secondary winding through the battery and back to point A. But the diode is now pointing against the current flow, and it will not allow the current to pass through itself. This breaks the return path for the current and stops the current from flowing anywhere in the circuit. Remember, we must have a complete path for current to flow in the circuit. It's a lot easier to understand how this circuit works if we look at a graph of the current that's flowing into the battery. When point A is positive, current flows through the diode and into the battery. But when point A is negative, the diode blocks the current, cutting off the negative half of the AC waveform. This is shown by the dotted line on the bottom, or negative half of the AC waveform. Because we're only using one half of the AC, just the positive half, this type of power supply is known as a half-wave power supply. By keeping the current flowing in one direction with the diode, we've changed alternating current into direct current. The output of this half-wave power supply is a special kind of direct current called pulsating DC. It's not pure and constant like the DC or direct current from a battery, but instead actually drops down to 0 volts and stays there for a full half cycle, or 1/120th of a second. To take advantage of both the positive and negative halves of the alternating current, we can connect 4 diodes together in a circuit called a bridge rectifier. Let's connect the bridge rectifier to the transformer's secondary winding and the dead battery. The 2 cathodes are joined together at the positive output of the bridge rectifier. You'll see bridge rectifiers drawn in all kinds of different ways. The only surefire way to find the positive output of the bridge rectifier is to see where the 2 cathodes are tied together. The positive output of the bridge rectifier is connected to the positive terminal of the battery. The negative terminal of the bridge is grounded, along with the negative terminal of the battery. The remaining 2 terminals of the bridge rectifier are connected to the secondary winding of the transformer. Let's trace the current flow when point A is positive and point B is negative. The current flows from point A to the junction of these 2 diodes. But which diode will conduct the current? Well, obviously the diode on the left is pointed the wrong direction against the current flow. So in this case, the current will flow through the diode on the right and through to the battery, giving it a little charge, and through to ground. The return path is from ground and again to the junction of these 2 diodes. Well, seemingly both of these diodes are pointed the correct direction. But remember, current flows from positive to negative, not from positive to positive. So the current flow will take the direction of this diode and back to point B, which is now the negative side of the transformer. When the transformer's polarity is reversed and point B becomes positive, the current flows from point B to the junction of these two diodes. Well, here again, the diode on the left is pointed the wrong direction, so the current flows through the diode on the right. Well, notice where this diode is going. This diode is pointed to the same point as the first diode allowed the current to flow through. That is, in this case, the current flows straight through and back to the positive terminal of the battery. Instead of simply cutting the current flow off, this diode acts like a detour and allows the current to flow back into the battery, giving it another little charge. Again, the return path is from the negative side of the battery to ground and back through to these two diodes again. Remember that current flows from positive to negative, so this time the current will flow through this diode and back to point A, now the negative side of the transformer. By using 4 diodes connected together as a bridge rectifier, we can use both halves of the AC waveform and charge the battery twice as fast. This type of power supply is known as a full-wave power supply. In fact, it's really known as a full-wave bridge rectifier power supply because it uses both halves of the AC waveform and uses a bridge rectifier as well. Instead of simply cutting off the current when it's flowing the wrong direction, as we did with the half-wave power supply, it's now rerouted by the bridge rectifier and flipped up to the positive side. Now the dead area between pulses of current is filled up with an additional pulse of current. Well, this makes the full-wave power supply much more efficient than a half-wave supply of the same voltage. It's important to note that although the full-wave power supply is more efficient than the half-wave power supply, the output still drops to 0 every half cycle. We simply have twice as many pulses as before. We find bridge rectifiers in the power supply unit of many games. This power supply from Williams Stargate has 3 on the printed circuit board. There's another way that we can make a full-wave power supply using just 2 diodes. This time, we'll use our center tap transformer and the 2 diodes connected in a circuit like this. Almost without exception, the center tap of the transformer will be grounded. The remaining 2 secondary leads are connected to the anodes of the 2 diodes. As with the bridge rectifier, we can find the positive output of the power supply where the 2 cathodes are tied together. The positive output of the power supply is connected to the positive terminal of the discharged battery. The return path is through ground and back to the center tap of the transformer. Let's trace the current flow in this circuit. When point A is positive and point B is negative, the current flows through this diode and into the positive side of the battery. The return path is through ground and back into the center tap of the transformer. When the polarity of the transformer is reversed and point B becomes positive, the current flows through this diode. Well, notice that this diode is connected right back up to the positive side of the battery. Again, instead of simply cutting off the current because it's flowing the wrong way, this diode acts as a detour and brings the current flow back up into the battery. The return path, again, is through ground and back into the center tap. Well, this is a way that we can make a full-wave power supply using 2 diodes. This type of power supply is called a full-wave center tap power supply because it uses a center tap transformer and both halves of the AC waveform. Notice something unusual about the way this power supply operates. When point A was positive, the current flowed through this diode and into the battery. The return path was back through to the center tap of the transformer. We only have used 1/2 of the transformer secondary. When point B becomes positive, the current flows through this diode and again back into the battery. The return path is through the center tap of the transformer again. This time we've only used this half of the transformer secondary. By using only 1/2 of the transformer secondary at a time, the output voltage of the full-wave center tap power supply will be 1/2 of the voltage of the entire transformer secondary. So in this case, if we wanted to charge a 12-volt automobile battery, we would have to use a 24-volt center-tapped transformer. A graph of the output of the full-wave center-tap power supply is the same as that of a full-wave bridge rectifier power supply. It's pulsating DC with 2 pulses for every cycle of the alternating current. We commonly see both types of power supplies in electronic games, and there's no clear-cut advantage of one over the other. A designer may elect to use either type or maybe even both in his game. What do you suppose would happen if we reversed the direction of the 2 diodes in the full-wave center tap power supply? Instead of having the 2 cathodes joined together, now we have the 2 anodes connected to each other. Well, do you remember what we said about the 2 anodes being connected together in the bridge rectifier? Remember, where the 2 anodes are tied together, we find the negative output of the power supply. By reversing the polarity of the 2 diodes, we've reversed the direction of the current flow in the circuit. By simply reversing the diodes, we've created a negative power supply. While the need for a negative power supply might not be immediately apparent to you, it will be as we look at other circuits later on in the course, especially when we look at asteroids. In the asteroids segment of the arcade school, you'll see how important those negative power supplies really are. Let's take our negative power supply and add 2 more diodes. Their anodes are connected to the transformer, and the 2 cathodes are tied together. Remember, where the 2 cathodes are connected together, we find the positive output of the power supply. By connecting just 2 more diodes, we can make a power supply that's both positive and negative. It's called a split supply. Because it's the transformer that determines the voltage of the supply, the voltage of the positive half of the split supply is equal to the voltage of the negative half of the split supply. They have the same voltage, but opposite polarity. Split supplies are very popular in video games. There's certainly no sense in using a separate transformer for your positive and negative power supply when you can make both supplies by adding just 2 additional diodes. This is a schematic diagram of the same split supply, but drawn in a different way. Does this look a bit more familiar to you? It's a bridge rectifier. Remember, you'll see bridge rectifiers drawn all kinds of different ways. In this case, the 2 diodes on the right are responsible for the positive power supply, and the 2 on the left for the negative power supply. Here's your clue for identifying a split power supply. Anytime you see a bridge rectifier powered by a center tap transformer, you're looking at a split supply. Now our power supply is really in pretty good shape. We can lower the voltage using the transformer and use 1, 2, or 4 diodes to change it from AC into DC. But we're not through with our power supply yet. We still have another problem. Remember I said that all of the computers in our games require 5 volts DC to operate. That 5 volts DC has to be exact. It can't vary very much. You have a tolerance of about 1/4 of a volt either way, but that's really about it. Well, if we look at a graph of our output from our power supply now, we can see that it's still pulsating DC. That is, the voltage still drops to 0 every 120th of a second. To help maintain a constant voltage to a game computer or a sound system, we use a part called a capacitor. This is a typical capacitor from an Atari power supply. The capacitor is this blue device right here. The capacitor is like a short-term battery that accepts a charge when there's power available to it, but when the power output from the diodes drops down to 0, the capacitor takes over and keeps that voltage constant across the rest of the devices in the game, such as the computer or the sound system. Here are some common schematic symbols for capacitors. The drawing on the left is the one you'll see most often. The others are variations of the first symbol. You'll notice that some of the capacitor symbols are marked with a plus sign on one end. Many capacitors are polarized, which means that, like a battery, there's a positive end and a negative end. If a capacitor is polarized, it will be marked with a plus or minus sign. It's easy to understand how a capacitor works if we do this simple experiment. I'm going to connect this capacitor to this lantern battery. When I connect the red clip lead, which is the positive lead of the battery, to the positive terminal of the capacitor should now be fully charged. It doesn't take very long to charge the capacitor. If I disconnect the battery now and connect it to this lamp, we should see the capacitor discharge across the lamp. And we should see the lamp glow very bright for a brief period of time and then dim out as the capacitor discharges. Watch. Pretty neat, huh? Well, let's connect this capacitor to our full wave center tap power supply and see how it operates in a normal working circuit. The positive lead of the capacitor, which you can identify by the straight horizontal line and the positive sign, is connected to the positive output of the diodes. We know this is the positive output because the two cathodes are tied together. The negative lead of the capacitor is grounded. Do you see the resistor that's been added to the output of the power supply? The resistor is labeled RL. This stands for load resistor. The load resistor represents whatever it is that the power supply will be powering. It could be a logic board or a sound system or a monitor circuit or just about anything else that uses direct current. Anything that provides power in a circuit is called the source. Anything that uses the power provided by the source is called the load. Let's look at the power supply now and see how it works. When the output voltage from the diodes is at its peak, current flows not only through the load, but into the capacitor as well. This charges the capacitor to the same voltage as the peak voltage coming from the diodes. When the voltage from the diodes drops, the capacitor, which is now fully charged, takes over to keep the voltage constant across the load. The capacitor acts as both a load and a source in a power supply. First it takes the current in as it charges, and then it becomes a source as it provides current to the load when the voltage from the diodes drops to zero. Well, as a result of adding the capacitor, the power supply no longer drops to 0 volts every 1/120th of a second. A graph of the power supply would now look like this. The peaks and valleys have been filtered out by adding the capacitor. In fact, we call a capacitor that's used this way in a power supply a filter capacitor. This graph shows what we'd like to see from a filtered power supply, a straight line that exactly duplicates the constant voltage of a battery. However, we're rarely so lucky in the real world. Because there's current being drawn from the battery during the time interval between pulses of current, the capacitor's voltage does drop a little between pulses. A graph of the filtered DC output might look something like this. The small fluctuation in voltage is something called power supply ripple, or hum. The term ripple comes from the fact that it looks like a rippled line when we see it in graph form, as we would if we were looking at the power supply with an oscilloscope. It's called hum because an audio system that's being powered by a power supply with excessive ripple will create a noticeable hum from the speaker. Finding a bad filter capacitor can really be a traumatic experience for some people, and it can be an impossibility for others. The fact of the matter is, though, that it's really easy to diagnose a bad filter capacitor. We'll be looking at the power supply filter capacitor test a little later on in the course. Well, suppose you found a bad filter capacitor. Naturally, you're going to want to replace it as soon as possible. Remember, downtime kills. And if you have a game with a bad filter capacitor, you better get it replaced right away, or your customer is going to be down the street playing a competitor's game. Well, like every other component that we've looked at so far, capacitors have certain specifications. So let's take a look at those capacitor specifications and see what they're all about. The first rating of a capacitor is its capacitance. The capacitance is simply a measurement of the amount of charge the capacitor can store. We measure capacitance in microfarads. The more microfarads a capacitor has, the more of a charge the capacitor will store. Typically, we see capacitors that are 20,000, 10,000, 4,700, or 1,000 microfarads. There are other ratings as well, and we'll see plenty of different types of ratings of filter capacitors as we look at different power supplies in different games. We use the Greek letter mu to denote the metric prefix micro, or 1/1,000,000th. But because the Greek letter mu looks a lot like our English letter U, you will often see capacitor abbreviations as mu-F, UF, MFD, or just plain MF. All of these ratings indicate microfarads, and the ratings will be printed on the capacitor itself and in the power supply schematic. The second rating of a capacitor is its voltage rating. The voltage rating of a capacitor is the maximum amount of voltage that the capacitor can stand across itself and still operate properly. For instance, if I have a 16-volt capacitor, I can use it in any circuit up to 16 volts, but I cannot exceed the 16-volt maximum. The voltage rating of a capacitor is not the amount of voltage the capacitor is putting out. The capacitor will only put out the same amount of voltage you put into it. The voltage rating of a capacitor is usually found on the capacitor itself or on the schematic diagram. This Williams power supply has two typical filter capacitors. This one's 18,000 microfarads, 20 volts, and this one is 4,700 microfarads, 35 volts. Well, when you go to a local electronics store to get a replacement capacitor, chances are not overwhelmingly good that you'll get an exact replacement. But you can get a capacitor that'll do the job for you. The general rule of thumb regarding power supply filter capacitors is that you can always go up in either capacitance or voltage, or even both. If you use a capacitor that has more capacitance than the one that you took out of the game, the power supply will just work that much better. If you have a capacitor with a higher voltage rating, the capacitor has better protection against high voltage failures. If, for example, you found a 4,700 microfarad 16-volt capacitor to be defective, and all you had was a 10,000 microfarad 25-volt capacitor in your toolbox, you could feel free to use the 10,000 microfarad capacitor as a replacement part for the defective 4,700 microfarad capacitor. Remember, we can always go up in voltage or capacitance, and in this case, we've gone up in both. Well, suppose you can't find a capacitor with a high enough capacitance rating. There's still a way you can get your game working for the weekend. Just get two capacitors and connect them in what's known as a parallel circuit. When you connect capacitors in parallel, their capacitance is added together. For instance, say I had an 8,000 microfarad 16-volt capacitor fail. But I go to the store and all I can find is 4,700 microfarads at 16 volts. The voltage is okay, but the capacitance isn't anywhere near 8,000 microfarads. Well, if I get two of the 4,700 microfarad capacitors and connect the two in parallel, their capacitances will be added together. 2 times 4,700 is 9,400, so we're well above the 8,000 microfarad limit there. When you connect capacitors in parallel, their voltage rating is unaffected. So what we end up with is one 9,400 microfarad 16-volt capacitor. And of course, we can easily use that to replace the 8,000 microfarad capacitor. It's easy to connect capacitors in parallel. Simply connect the two positive leads to each other and do the same with the two negative leads. Well, now we know how our power supply works, with a transformer to change the voltage, rectifiers to change it from AC to DC, and capacitors to filter out the pulsating DC, keeping the voltage pure. Well, believe it or not, we still have one more thing we have to do to our power supply before we send it to the computer. Remember I said that all of the computers that we use in games require an exact 5-volt power supply. And it can't vary very much. Plus or minus 0.25 volt, or 1/4 of a volt, is about all we have either way. If the voltage starts to drop below 4.75, or it goes above 5.25 volts, the computer will probably start to malfunction. Well, remember that the power supply is simply taking the 120 volts from the power receptacle, changing the voltage and filtering it. And remember too that the power that comes from the wall receptacle is not particularly constant in terms of its voltage. And it can fluctuate plus or minus 10%, and in fact it does quite often. The voltage in this shop varies quite a bit. Sometimes it's 108 volts, sometimes it's 124. So because that voltage isn't very constant, we have to regulate our power supply. The voltage regulator keeps the output voltage of the power supply at a constant 5 volts regardless of what happens to the 120 volts AC input. The simplest type of voltage regulator used in games is something called a 3-terminal regulator. And this is a popular 3-terminal regulator. Notice it comes in a TO220 package, the same package that we saw earlier as a transistor package. However, this is a voltage regulator and it's actually an integrated circuit. You remember we looked at all those different types of transistor packages? And remember that they had different transistor outline numbers, TO3 and TO220 and so on. Well, those packages are really pretty standard for all semiconductors, and that particular package might contain an integrated circuit or a voltage regulator or a transistor. The only way you can tell which is by looking at the part number that's on it. It's just like these milk cartons, where the cartons are identical, but they contain different products. This is vitamin D milk, and right next to it is buttermilk. And right up here is something called sweet acidophilus, whatever that is. They're all in identical cartons, and the only way you can tell the difference between them is by reading the label. It's the same way with electronic parts. Those packages that we have are really quite standard. The only way you can tell if the part is a transistor or an integrated circuit is by reading the part number. This regulator is one of the 78 series of 3-terminal regulators. These are positive regulators that can regulate up to 1 amp of current. They come in a variety of voltages, and the voltage of the regulator is indicated where the two X's are. By reading the part number on this part, we can see that it's a 7805, which is a plus 5 volt regulator. But we also use 7812 and 7815 in games. In schematic form, the voltage regulator is generally drawn as a rectangle. The voltage regulator is installed in the power supply after the diodes and the filter capacitor. That is, after the current has been rectified by the diodes and filtered by the filter capacitor, it's then regulated by the voltage regulator. The way the 3-terminal regulator works is quite simple. No matter what you put in, the output stays at exactly 5 volts. Well, it's not really quite that simple. There are a couple of qualifications that we have to look at, and one of them is the input voltage has to be at least 2.5 volts higher than the 5 volt output. You can't put 3 volts in, for instance, and expect to get a regulated 5 volt output. But they usually use a much higher voltage in than out, so that in case the line voltage from the 120 volts AC drops somewhat, at least the output will remain constant that way. As long as the input is at least 7.5 volts, the output will remain at exactly 5 volts DC. Also, remember that this is called a 3-terminal regulator. Well, the input accounts for one terminal and the output the second. But the third terminal is common or ground and must be grounded for proper operation of the regulator itself. Knowing the connection points of the regulator can really help speed troubleshooting when you're working on a power supply. And this is the connection diagram for the 78 series 3-terminal positive regulators. Notice the common lead is in the center with the input and output on either side. Notice too that the metal tab of the regulator is also a common connection. There's another type of regulator that you'll often see used in place of the 78 series regulators. And these are the LM340T series. As before, the voltage is indicated by the number following the T. Thus, the LM340T-5 is a plus 5 volt regulator, and so on. Both parts are interchangeable, and you may even see a single device with both the 78 series and the LM340 series number printed right on it. This Stern power supply is typical of most that use 3-terminal regulators. And here we see 3 regulators mounted to this black aluminum heat sink. There's a common problem that we see in video games that recurs quite often in power supplies. and this comes under the heading of diagnosing a bad filter capacitor. A lot of mechanics have quite a bit of trouble repairing power supplies when they have a bad filter capacitor. The reason being that you see all kinds of strange readings, and if you don't know what to expect, you really don't know how to interpret the readings that you make. So let's take a look at this power supply and see what happens when we have a bad filter capacitor. When a filter capacitor fails, it generally loses its ability to hold a sufficient charge. This allows the input voltage to the regulator, which is shown here by the graph on the left, to drop below the 7.5 volt minimum required to maintain our 5 volt output. When the input voltage drops below the 7.5 volt minimum, the output voltage of the regulator drops as well. And we can see by the graph on the right that the voltage has dropped below the 5 volt minimum required by the computer. Now let's see how the average mechanic might tackle this problem. Anytime you have bizarre problems with your game and you don't know where else to turn, start by checking the power supplies. Knowing that power supplies are responsible for a large percentage of the failures in games, our average mechanic checks the power supply across the power rails on the printed circuit board. But the meter doesn't read 5 volts. The meter only reads 4.5 volts. That's because the meter is averaging the times when the voltage is up at 5 with the times that the voltage is allowed to drop lower because of that defective filter capacitor. The meter averages out the two and shows us a reading of 4.5 volts. Although the meter shows us a reading that seems to indicate our problem is a low voltage coming out of the regulator, we know that our problem is really caused by a bad filter capacitor. Well, we have a saying in electronics, and the saying is garbage in, garbage out. What that means is that when we encounter a bad output from a device or a circuit, before we change that device or repair the circuit, we want to check the input to it to determine if it's good or not. Certainly you wouldn't expect a device to have a good output if the input was bad. Knowing this, and based on the incorrect assumption that the problem is low voltage from the regulator, our average mechanic then checks the input to the regulator and finds it to be slightly under 9 volts DC. The average mechanic's no fool, and he knows as long as he has at least 7.5 volts as an input to the regulator, the output should be a constant 5 volts. Since he's tested the input and he has at least 7.5 volts, and he doesn't have a good 5 volt output, he assumes the device to be bad and changes the regulator. Of course, when he fires the game back up again, he has the same problem as he had before because he changed a good part. And you certainly can't expect the game to work any better when you change a part that's already good. It still looks like a low voltage problem, and now our average mechanic is starting to get a little confused. On one hand, 8.9 volts as an input should be plenty to get exactly 5 volts out. And on the other hand, our average mechanic knows that the input to this regulator is normally somewhere around 12 volts. Could this mysterious drop in voltage have anything to do with the problem? Well, again, our average mechanic is no slouch when it comes to fixing games. So he thinks to himself, gee, I wonder what's wrong. Maybe the diodes are bad. So he checks all 4 diodes in the bridge rectifier with his meter. The bridge rectifier tests good, but he changes the diodes anyway. Now, naturally, when he fires the game back up again, he still has the same problem. Believe your meter. If the meter tells you your diodes are good, they are good. And if it tells you the diodes are bad, they are bad. So far, our average mechanic has replaced the regulator and the bridge rectifier, and he still hasn't found the problem or repaired the game. Boy, now our average mechanic is really starting to get upset. He knows he has a voltage problem somewhere, but as far as he's concerned, the only device left that has anything to do with voltage is the transformer. So he goes to his boss and says, gee, boss, we have to order a new power transformer. Well, quite frankly, power transformers don't fail too often, and it might be a while before you actually get one in stock. So they bring the game back into the shop and they wait a couple of weeks, and the mechanic sets aside a half a day to install the transformer. He installs the transformer, fires up the game, and same problem. Well, naturally, again, he's changed a part that's good. Transformers don't fail very often. In fact, next to the cabinet of the game itself, the transformer is probably one of the most reliable parts in the game. So now the regulator, the bridge rectifier, and the transformer have all been changed, and the game still isn't working properly. By process of elimination, our average mechanic finally decides that his problem must be a bad filter capacitor. It's the only part left. So he changes the filter capacitor, and lo and behold, the game starts to work properly. He says to his boss, "Boss, it turned out to be a really tough problem. It was a bad filter capacitor." Well, diagnosing bad filter capacitors is actually quite simple. Believe me, I know. That average mechanic was me. You only have to go through a fiasco like that once before you find a better way to diagnose a bad filter capacitor. When the bad filter capacitor causes excessive ripple in the power supply, one of the symptoms is a lower than normal reading at the output when you check the DC voltage. Well, standing alone, the DC measurement can point to either of two possible failures. Either the DC output of the regulator has indeed dropped due to a regulator failure, which would be the obvious first guess, or the low DC reading is being caused by excessive ripple in the power supply as a result of the defective filter capacitor. When you make the DC measurement, you have no way of knowing which of the two possible causes are creating the low reading that you see. But by switching your meter over to read AC volts, the meter will automatically ignore the DC voltage and show you the ripple in the power supply as AC. Normally, you should see no alternating current in a properly working DC power supply. Well, here, when we've switched the meter to read AC, we see 0.6 of a volt of AC ripple. Obviously, we have a ripple problem in this power supply, and ripple is almost inevitably caused by a bad filter capacitor. The importance of this test cannot be overemphasized. Whenever a power supply voltage reads lower than expected, be certain that you switch your meter to read AC volts to find out if this low reading is caused by low voltage or ripple. If you see very little AC, then your power supply is clean, and your problem is simply low voltage. However, if you switch your meter over to AC and you read an excessive amount of AC voltage, your problem is more than likely a bad filter capacitor. Of course, the big question is, how much AC is considered excessive? Well, we see power supplies in a number of different voltages, and the ripple has to be expressed as some kind of a percentage compared to the DC voltage of the power supply. Generally speaking, in a regulated supply, the ripple content will be less than 1/10 of 1% when the supply is operating normally. In an unregulated power supply, or on the unregulated input of a regulated supply, the ripple can actually be as high as 5%, and the unit will still function properly. However, if you start to get up around 5% ripple, chances are pretty good your capacitor is starting to fail, so keep an eye on it. I try to use about 3% as the figure, and if it goes over 3%, I usually change the filter capacitor. If the output voltage of the regulator does read too low on DC, but there's no AC when you switch your meter to read AC volts, remember, check the input voltage first before you change the regulator. Remember, garbage in, garbage out. But if we read a good input, in this case 12 volts DC in to a 5-volt regulator, and a low DC output with no ripple, then the regulator itself has to be the cause of the problem. Negative power supplies have to be regulated too. Many of today's video games have a minus 5-volt power supply. But we can't use the same regulators for the negative supply that we do for the positive supply. The negative regulators are the 7900 series. The voltage rating of the negative regulators is indicated by the last two digits. So 7905 is a minus 5-volt regulator, 7912 a minus 12, and 7915 a negative 15-volt regulator. And again, we have another set of part numbers that you might see used as a substitute. They're the LM320 series, and the last two digits indicate the voltage of each of these regulators as well. Negative regulators are not interchangeable with positive regulators. Notice the difference in the connection points here. The output pin has remained the same, but the input and common leads have been reversed. Notice too that The tab of the device is now the input of the regulator. This is a negative voltage regulator on Atari's Asteroids printed circuit board. Because the tab of the regulator is also the input, the grounded metal backing has been cut away from behind this regulator. By using a split supply and 4 voltage regulators, we can create 4 separate regulated power supplies. Here we have 3 positive regulators creating a +5, +12, and +15 volt supply. And the negative regulator we just looked at, which is a 7915, is used to create a -15 volt supply. Notice too that the capacitor in the negative supply is apparently connected backwards. The positive terminal of the capacitor is grounded. This is extremely important because remember, a capacitor is polarized. In a negative supply, the filter capacitor will always be connected this way. If we take another look at this printed circuit board, we can see the 4 diodes that are the bridge rectifier, the 2 capacitors, and notice they're installed in opposite directions because one's for the positive and one's for the negative supply, and 3 of the 4 regulators, the 7915, the 7805, and the 7815. The positive 12 volt regulator is located elsewhere on the board. Some types of 3-terminal regulators are adjustable, and this is the type 317 adjustable 3-terminal regulator. The adjustable regulator is used where the manufacturer of the game needs an output voltage other than the fixed 5, 12, or 15 volt output of the regulators we just looked at. Midway uses a type 317 adjustable regulator in this power supply to obtain a 7.2 volt output. Here the regulator is drawn as a circle instead of a rectangle. You might even see a 3-terminal regulator schematic drawn as a triangle. The decision to draw the 3-terminal regulator as a rectangle, a circle, or a triangle is really arbitrary, and it's up to the draftsman who draws the schematic. The output voltage of the regulator is determined by these 2 resistors, and by changing the value of these resistors, the output voltage of the regulator can be adjusted. The connection points of the type 317 regulator are different from those we saw earlier. In the 317, the output of the regulator is the center lead and the tab, and the input and adjustment leads are on either side. By the way, you may see the part number listed as either LM317 or UA317. The different 2-letter prefixes are determined by different manufacturers. Some manufacturers of the same part use LM, others use UA. We can pretty much ignore any 2-letter prefix on a part number and just look at the number itself. The 3-terminal regulator is really a nifty device. All we need to do when we want a regulated supply is to run an unregulated voltage into the regulator and take our regulated voltage out. But there are times when we can't use a 3-terminal regulator. One of the places we can't use a 3-terminal regulator is when we need a very high voltage. The highest voltage that we see in the 3-terminal regulator is 15 volts. So when a video game or electronic pinball manufacturer wants a higher voltage, they have to use something else besides the 3-terminal regulator. Also, when the manufacturer needs a supply that's a higher current supply, again, they can't use the 3-terminal regulator. The 3-terminal regulator is really quite limited in its current capability. And generally, 3 amps is about the highest we ever see in terms of a current rating for a 3-terminal regulator. Also, there are times when the manufacturer wants to include some kind of a protection circuit in the power supply. For instance, there's a protection circuit that many video game manufacturers use that automatically shuts off the power supply if the computer board shorts out and draws too much current. That protects the power supply and keeps it from burning up. In all 3 of these conditions, we cannot use a 3-terminal regulator. We have to use something else. And the part that we use is a transistor. This is known as a series pass regulator circuit. And in the series pass regulator, the unregulated input voltage is connected to the collector of the transistor, and the regulated output voltage is taken from the emitter. But how can a transistor function as a voltage regulator? Let's take a close look and find out. In this circuit, we're trying to obtain an output voltage of exactly 5 volts DC as a power supply for the game's computer. The input voltage at the collector of the transistor is around 12 volts DC. Remember, the input voltage of a regulator circuit is always considerably higher than the output. Well, what will the output voltage be if the regulator transistor is turned completely on? If the transistor is fully turned on, it shorts out between collector and emitter. This lets the 12 volts pass straight through the transistor, making the output of the power supply 12 volts. If we connect this power supply to the computer, we'll probably do some costly damage to the system. So we cannot allow the series pass regulator transistor to become fully turned on. What would the output voltage be if the transistor was completely turned off? Well, if the transistor is turned off, no current passes from the collector to the emitter, and the output voltage would be 0 volts. To get exactly 5 volts out of the power supply, the transistor has to be turned on about halfway. If the transistor is turned on too hard, the output voltage will be much too high. And if the transistor is not turned on hard enough, the output voltage will be much too low. Seems like a tough job, doesn't it? Well, as usual, the things in electronics that seem difficult are really quite simple. To keep the output voltage at exactly 5 volts, all we have to do is put 5.7 volts on the base of the transistor. With 5.7 volts on the base of the series pass regulator transistor, the output voltage must remain at a constant 5 volts. Remember, the base of the transistor always compares itself to the emitter voltage, and in an NPN transistor, the base has to be 0.7 of a volt higher than the voltage at the emitter in order to turn the transistor on. With 5.7 volts on the base, the output voltage cannot vary above or below 5 volts. This system is not limited to just a 5 volt power supply. We use the series pass regulator system for many different voltages. For instance, we might have a circuit where 20 volts was the input, and with 12.7 volts on the base, we would get exactly 12 volts as an output. In our monitor circuit, we have 145 volts as an input, and with 120.7 volts on the base of the series pass regulator transistor, the output remains at a constant 120 volts DC. Of course, the big question is, where does the 5.7 volts come from? Aha! The answer is simple. It's an integrated circuit, a special type of integrated circuit that's specifically designed to put exactly 5.7 volts right on the base of the transistor. The output of the integrated circuit is connected to the base of the series pass regulator transistor. This integrated circuit does not have enough current capability to drive the computer itself, but by driving the series pass regulator transistor, we can make a precisely regulated power supply with exactly 5 volts out that can handle the large amount of current needed by the computer. One popular type of integrated circuit used to drive the 5 volt series pass regulator transistor is this one. It's part number 78GU1C. This particular regulator IC is used to drive the 5 volt series pass regulator transistor in a Stern power supply. And here's the schematic diagram of that supply. Here's the regulator transistor, and here's the voltage regulator integrated circuit that drives it. The 78GU1C is a 4-terminal regulator. Pin 1 is the common input, which is normally grounded. Pin 2 is an unregulated input. Pin 3 is the regulated output that's connected to the base of the series pass regulator. And Pin 4 is the control input, which allows you to precisely adjust the output voltage of this regulator. Williams uses a different type of integrated circuit to power the regulator in this power supply. It's the type 723. Here, the 723 is used to power the series pass regulator that creates the 12 volt power supply in the game. The 723 can also be used to power the 5 volt power supply in the game. But the 723 cannot provide enough current to drive the high current series pass regulator transistor. In order to use the 723 in the high current 5 volt power supply for the computer, The 723 is used to drive a low power transistor, which in turn is used to drive the series pass regulator transistor itself. Does this transistor circuit look familiar to you? It's a Darlington circuit, isn't it? And here on the Williams schematic, for the power supply itself, we can actually see that they've used a Darlington transistor as the series pass regulator. And here's the transistor itself, mounted on the heatsink of the power supply board. Gee, how do we troubleshoot power supplies that use integrated circuits and transistors? As usual, it's simple. We'll do it the same way we did it before. That is, we'll start by checking the output of the power supply. Remember, that's the way we do things. We start at the output and work our way back. If we start at the output and measure the output voltage and say it reads too low, remember, you're going to switch your meter to read AC ripple and see if you have AC ripple. If you do, then you have to suspect the filter capacitor is bad or even possibly disconnected. Bad solder joints often cause the filter capacitor to become disconnected, causing excessive ripple. But if you measure the output voltage and it reads too low, but there's no AC, remember, garbage in, garbage out, you're going to check the input and see if it's good or not. If the input's good and the output's bad, obviously the problem is in the regulator circuit somewhere. Well, once you have determined exactly where the problem is, simply turn off the game and check the parts in your power supply. You know how to check transistors. There's 2 transistors in the power supply. Check both the transistors. If they both check good, change the regulator. I guarantee you, you'll be able to find the problem. It's easy to determine which parts in the power supply have failed, and it's just as easy to obtain replacement parts. Wico is your one-stop replacement parts headquarters for all the electronic components that we use in games. And here in the Wico catalog, you'll find all the electronic components that you need listed not only by the manufacturer's part number, but also by the generic part number of the part itself. In the front of the catalog, the parts are listed by part number, and in the back of the catalog, they're listed by each manufacturer's type number. Once you've determined which parts you need, just pick up the telephone and call Wico. There's a toll-free number for each of the 6 Wico outlets.
We're Wico, world's largest distributor of parts and supplies to the amusement, music, and vending industries.
There are some high-voltage power supplies that we use in games that have to be regulated as well. For instance, the Bally and Stern pinball machines have score displays, and these score displays require about 190 volts to operate. But that 190 volts has to be regulated. It can't fluctuate very much. Well, we can't use the 723 to regulate a high voltage. The LM723 is strictly a low voltage regulator IC. When we want to regulate a high voltage power supply, we can't depend on those integrated circuits. So we have to make the supply out of discrete or individual transistors and resistors and diodes. This circuit is typical of those that we'll find not only in the pinball machines, but also as the power supply regulator circuit in monitors as well. It's a standard series pass regulator circuit with a regulator transistor and a driver transistor in a Darlington setup, but instead of using the integrated circuit, we use a transistor and a Zener diode. Overvoltage protection circuits are built into some power supplies to prevent a shorted regulator from damaging the computer. In this power supply, a 5-volt output is being sent to the computer. But suppose the regulator transistor shorts out. Well, this will cause 12 volts to be applied to the computer, and it won't take very long before the entire computer board is destroyed by the excess voltage. To prevent a shorted regulator from damaging the computer, some game manufacturers have included a circuit called a crowbar. The crowbar circuit is made of the Zener diode and the SCR with a small handful of other components. Under normal circumstances, the Zener diode will not be conducting. It's a 5.6 volt Zener, and a normally working power supply like this will have an output of just 5 volts. But if the regulator were to short circuit, causing excessive output voltage, the Zener diode will start to conduct and gate the SCR. When the SCR is gated or turned on, it conducts directly from the output of the supply down to ground and shorts the power supply output immediately to ground, which of course is 0 volts. This protects the computer from any excessive voltage. Boy, it's a good thing that games are easier to repair than they are to play. You can see that the regulated supplies that we use in video games and pinball machines aren't particularly difficult to understand. And once you understand how they work, and with those all-important meter tests that we looked at earlier, there's no reason that you can't repair any regulated power supply in any electronic game. Well, that's all the time we have for now. I'll see you next time at the Arcade School. Bye-bye.